All right, guys, we're going to go ahead and take a look at the lesson 1.3. Okay, a little bit more information about limits. Okay, I want you guys to look at this real quick. All right, and we're actually going to look at the graph of that in a minute. But when we have this all factored out, and if I'm able to cancel that out right there, what is happening is that at x equals 1, okay, if I plug in 1, we've talked about this a little bit in class, right? At x equals 1, I get 0 over 0. 0 over 0 is what tells me that this has a hole in the graph. Okay, so let's go ahead and go take a look at this. If I look at this graph, and we're talking about at x equals 1. Okay, so don't worry about the rest of it here for a sec. Let's just look at what's happening at 1. Okay, as I come this way, you can see it's approaching a certain number. But when I get right to 1, there's a hole in the graph. It's undefined. Okay, and holes in the graph come from 0 over 0. All right, so I have a hole in the graph. Now, when I reduce this down, so here's my new, now that I crossed that off, here's my new equation. Let me write it right here. In this, the notation it uses here is like RED, reduced. Okay, it would have an x minus 2 squared and an x minus 4 to the third on the bottom. Okay, this book calls these even or odd vertical asymptotes, all right? When you have a number over 0, and there's a number on the bottom, it's not a hole anymore, now it's an asymptote, okay? A straight up and down asymptote. So I can see that I have an asymptote right here at x equals 2 and x equals 4. Okay, it's just like you solve them, right? You do like the opposite, the same that I would do up there with the hole. Okay, at 2 and 4. Now look at what's happening. Let's go back here. At 2, think about our limits, okay? I'm going to do it like that. There we go. Okay, as I'm approaching 2 from the left, it's going down. As I'm approaching 2 from the right, it's going down. But you see how the things are going in the same direction? That is called an even asymptote. Oh, it already said x equals 2. Now let's look at 4. At 4, from the left is going down, from the right is going up. That is called an odd asymptote. All right? Now, how do I know? So even will go the same way, odd will go opposite ways. How do I know? Literally, guys, just from the exponent. If it's a squared, it's even. They're going to go the same way, maybe up, maybe down. Kind of depends, right? If it's a third, they're going to go opposite ways, maybe like that, maybe like that. So it shows you some examples of even or odd asymptotes. Okay, it kind of helps us to like look at this stuff when we're thinking about graphs. All right. Okay, so real quick, we're going to start talking about asymptotes. And you guys, this is where I get a number over 0. We would typically write this as undefined or DNE, okay? So I kind of want to look at the graphs here, like some of these. So even if you're finding one-sided limits, even odd asymptotes and holes. Okay, great. Let's take a look at this first example here, you guys. And I'm going to teach you how to do this without looking at the graphs, but we can kind of think about the graphs real quick. Step 1 with numerical limits is we always just plug it in. The fact that it says 2 from the right, I'm not going to worry about that right now. I'm going to plug it in. And when I plug it in, I get 5 over 0, which tells me that there is an asymptote at 2. All right. Now, does the asymptote, oh, and if it helps you, I mean, it's an odd asymptote, which means they're going to go different directions. Okay. X plus 3 over x minus 2. All right, let's take a look at that. Let's go x plus 3 over x minus 2. All right. And we know we have an asymptote at x equals, oh, just regular 2, actually. Let me turn this into an asymptote real quick. Okay. Now from a graph, I can see that from the right, I'm going to positive infinity. From the left, I'm going to negative infinity. Like I can see that on a graph. What if it doesn't give me a graph? There's actually a pretty easy way to do this, all right? Okay, as I'm approaching 2 from the right, this is a number slightly bigger than 2, 2.0001 maybe. Okay? 2.0001 plus 3 is a positive number. It's like 5.0001. Okay, 2.001 minus 2 is also a positive number. It's like 0.001. This is going to infinity, but how do I tell if it's a positive or negative? That was a terrible infinity. Hold on. How do I tell which way the asymptote is going? Well, right here, it's a positive number and a positive number, so it goes to positive infinity. So as I approach 2 from the right, it's going to positive infinity. And I can tell by just checking my signs, okay? So same question here from the left. Now, if I'm looking on the graph, I could be like, okay, from the left, it goes to negative infinity, but I want you guys to be able to do it without necessarily looking at the graph, right? So here's how I do this. I'd go, okay, a number that's just barely to the left of 2. How about 1.999, right? That's a positive. Minus 2, that's a negative. Positive divided by negative is negative, so it goes to negative infinity. Okay, that's how I can figure out these asymptotes actually pretty easily, is by looking if they go, by plugging in a number really close on the other side. All right. Okay, perfect. Now this one has, if I were to go plug in 1, right, I would get negative 1 over 0. So there's an asymptote at x equals 1. Okay, I'm not even going to graph it right now. But what I know about this asymptote is it's an even asymptote because it's squared. So it means they're going to go up, up, or down, down. They're both going to do the same thing. So how do I decide? So I know it's going to go to one of the infinities. How do I decide positive or negative? Okay, well, we're looking at 1 from the right. It means slightly bigger than 1. That's like 1.001. We'll do that. 1.001 minus 2 is a negative number. 1.001 minus 1 squared is a positive number, so that asymptote's going to go to negative infinity. Okay, so without even looking, I'm able to tell. Now, if you guys remember, it kind of talks about up here, with one-sided limits, we're usually going to put positive or negative infinity. Remember, any single answer here, though, I could also just put DNE, and I would be correct, because technically infinity doesn't exist, right? So we're trying to be good, and we're going to try to talk about like where they go to by the asymptotes, but a lot of times it might just say DNE. Okay, same question from the left. All right, same question from the left. So that's like 0.999. Well, 0.999 minus 2 is negative. 0.999 minus 1 is also negative, but when I square it, it's positive. So negative divided by a positive is a negative. So look at what happens here, you guys. Both to the left and the right of 1, both go down. And that's why it's an even asymptote. So we're expecting those to go the same way. Okay. Now don't get tripped up on here. We always plug in first. And when I plug this in, I get 4 minus 4, that's 0, 2 minus 2. So I get 0 over 0. This is not an asymptote, right? What is it? This is a hole in the graph. So this is why I always start by plugging it in first, because it tells you what to do next. And I know that the thing that I do next on here is I factor. Okay? And cancel. And I got rid of the hole right there. So now I have the limit as x approaches 2 of x plus 2. And now when I evaluate it, 2 plus 2 is 4. So that's not an asymptote question. That's actually a hole in the graph. All right? So hopefully that makes sense. So the big thing that you want to remember from this, which we can put up here, 0 over 0 makes a hole. All right? A number over 0 makes an asymptote. And we got to figure out which infinity it goes to. Okay? All right, awesome. Let's go skip to this next part. All right, you guys. Now, we are going to talk about limits to infinity. Okay? This might start off by being a little confusing, but I'm going to try to make this as clear as possible. Are you ready? We have numerical limits. Okay, and this will just be a little bit of a review for you. With numerical limits, we have, and a numerical limit, by the way, is the limit as x approaches some number. Okay, and here's what we got, you guys. Step one, you always plug it in. Okay, always. We plug in that number. That kind of tells us what to do next. If we get an answer, good, we're done. If not, here's what we do. If it's 0 over 0, we're going to do factoring or conjugate. If it's a number over 0, it's an asymptote, which means that it either goes to positive or negative infinity, and we just kind of have to check the graph or plug in numbers very close or whatever. That's it for numerical limits, okay, you guys? That's basically what we're looking at. Now, when we're talking about infinite limits, okay, I think this explains it a little bit better, so I'm going to explain it like this. Infinite limits are where we have the limit as x approaches infinity or as x approaches negative infinity. Let's look at a graph really quickly to interpret an infinite limit, okay? All right, this graph right here has, aside from a vertical asymptote, it also has a horizontal asymptote, all right? And I believe the horizontal asymptote is at 1. Let's check. Yes, it is. That looks good. Make that dashed, all right? So the horizontal asymptote is at 1. And so look at what's happening as I go out to infinity. You guys see? Let me zoom way, okay. Get really close here. As I go to infinity, as that number gets bigger and bigger, I'm getting closer and closer to 1. As I go to negative infinity, I'm getting closer and closer to 1. You know, and we can't see it until we like zoom way, way, way out there and get a point or whatever. Gets closer, closer to 1. Okay? And then same on this side, closer and closer to 1. So our horizontal asymptotes tell us what happens at the outsides of the graph. This, you guys, is called end behavior. Okay, so as an example real quick, it's like, let me just draw, I don't know, an asymptote here, okay? This is basically what's happening at the ends of the graph. Not the top and bottom ends, the left and right ends. So infinite limits is here and here. Okay, those are where my limits to positive and negative infinity are. And it's basically finding those horizontal asymptotes. So you may have learned this before. Here's how it works though, okay? When we're looking at rational functions, if you have the degree of the bottom and it's bigger than the degree of the top, all right, it always gets to go to 0. The limit is always 0, all right? Because what's happening is, let's take this same equation here. If the bottom is bigger, so let's say I make that like x squared, right? Look, that's approaching 0. That crosses, but then it still comes back and approaches 0, all right? Because I'm dividing by a very big infinity. I'm dividing by an infinite number. So it gets smaller and smaller and smaller, okay? Okay, the next one is if the degree of the top equals the degree of the bottom, right? If the top and the bottom are equal to each other. Well, what we do, you guys, is we use the coefficients. Okay, so let me show you some examples real quick that I think will help it make sense. Okay, so let me get rid of that squared. So these are now, the top and bottom are equal because it's x to the first and x to the first. And we found out that my horizontal asymptote was at 1. Okay? All right, let's change this. Let's put a 6 over 2. I said 2, I put 5. 6 over 2. The coefficients of the x, 6 over 2, 6 divided by 2 is 3. What that does is that changes that to a 3. That's just how it works. Okay? Let's say I do a negative 10 over 5. Negative 10 over 5 is negative 2. Moves it down there. All right, as long as the x's are the same. Now, even if I put like x squared and x squared, it's still going to have that asymptote at negative 2. As long as they're the same, the degree of the top, the degree means the highest exponent, and the degree of the bottom, we use coefficients. The last one, if the degree of the top is bigger than the degree of the bottom, what happens is this is going to tend towards positive infinity or negative infinity. And it actually doesn't make a horizontal asymptote. I don't know if you guys have ever learned these before. It makes what's called a slant asymptote. Let's get this back to the beginning. There we go. So that doesn't have a horizontal asymptote. It has a slant asymptote. You can kind of see it. So what's happening as I go to positive infinity? It goes to negative infinity. And as I go to negative infinity, it goes to positive infinity. Okay, so that's how those work. So let's look at some examples. It really is this simple, you guys, all right? But this, you want to know that, okay? Okay, so here we go. And horizontal asymptotes come from the limit as x goes to infinity. It's the exact same thing. So I don't know if you guys even remember doing these horizontal asymptotes. So these are basically the same questions. And right here, okay, x4, x4, those are equal. So I'm going to have an asymptote at 5 over 10 or 1/2. Okay. This one has an x to the 4th and an x to the 5th on the bottom. So I'm going to have a horizontal asymptote at 0. Right? And then this one is bigger on the top than the bottom. So it's not going to have a horizontal asymptote. It actually has what we call a slant asymptote. Okay? That's going to have a slant asymptote. There's a way to find the equation of it, but we're not going to do that. All right? Now, check this out. Let's do limits. Guess what? You find it the exact same way. It's just not an equation. Look, the degree of the top and bottom are the same. The limit is the coefficients, 5 over 10 or 1/2. That's my limit. Super easy, right? If the bottom is bigger than the top, it goes to 0. Now, does it matter that it's to negative infinity? Not when it's going to 0, because positive, negative doesn't matter, right? All right, top bigger than the bottom. Now, this goes to positive or negative infinity. So how do I decide which one? Okay, you check your signs. Here's what you do. If I have a very large positive number to the 4th, that's positive. By the way, I ignore all this. I don't use it. If I have a very large positive number to the 3rd, that's positive. A positive divided by positive is positive. So I get positive infinity for that. So you just check your signs on your two biggest terms. All right? That's literally how easy this is. Okay, that's literally how easy this is. Now, look at the example of number 12, and it has a note here. Make sure you consider the highest degree of the terms, not the highest degree of the factors. You guys, in order to do this problem, I'd have to multiply this all out. Okay? Now, do you want to multiply that all out? That looks crappy, right? Like, I'd have to do x minus 1 times x minus 1, and I'd have to FOIL that, and then I'd have to multiply that by that, and it would take forever. Okay, but look, if I FOIL that out, I only care about the first term, and the first term is x squared. And over here, the first term is 2x. And so all together, guess what the first term is going to be? It's going to be 2x to the 3rd, blah, blah, blah. Don't care. Right? I don't care what the rest of it is, because when you're going to infinity, it's only by the biggest terms. That's all that's making it go to where it's going to go. Okay, let's square this. Well, if I were FOILing this, 3x times 3x would be 9x squared. That's x. So this would start with 9x to the 3rd, and then blah, 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 a bunch of crap. Right? The degree of the top and the bottom are equal, so I use coefficients. So this one has an asymptote at 2/9, and the limit as I approach infinity is 2/9. Okay, infinite limits are actually really pretty easy. Okay, there's only one little thing that can happen that's kind of weird, and we're going to look at that example on 13 and 14. Okay, now remember we talked about how, when we're doing these limits to infinity, we're really only looking at the biggest term. Like you guys, infinity minus 3, in fact, infinity squared minus 3, that's not going to do anything, right? So it's going to tend towards this. Now, the square root of 4x squared is 2x, because we just kind of ignored that. We can only do this with limits, guys, and x. And guess what? Same exponent, x to the first, x to the first. And so I use coefficients, and I get 2 over 1, or 2. And that's my limit, okay? Now, here's the issue. We were plugging in right there a negative infinity, but something interesting happens when we were plugging in a positive infinity. Something interesting happens when we plug in a negative infinity, okay? So I get rid of that, all right? I know that the square root of 4x squared is 2x. Same degree on the top and bottom, so it's 2 over 1, so it's 2. But here's what happens, okay? Because I did the square root of a squared, right? Okay, I'm still ignoring that. If I take a negative infinity squared, that's a positive. The square root of that is a positive. And if I take a negative infinity and put it down here, I get a negative. Positive divided by negative is negative. So, for this particular equation, on one side it goes to positive 2, one side it goes to negative 2. I'll show you guys what this looks like. Okay? So this was it was square root of 4x squared minus 3 over x. Okay, interesting domain there, right? Some stuff is missing in the middle. But look, as I go to infinity up here, what's it getting very close to? 2. As I go to infinity down here, what's getting very close to? Negative 2. So you can kind of see how that works. So you got to be really careful when you see those square root squareds. All right, cool. Guys, the next thing we're going to talk about is, it says use the end behavior of e to the x to find these limits. Okay, this is interesting stuff. You kind of have to know what the graph of e to the x looks like, right? And eventually, you guys, I really would want everybody to be able to graph that, like just boom, right off the bat, okay? If I kind of forget how to do it, all right, remember this. There are 2 things that I want you to remember for e, and it's e to the 0 and e to the 1, okay? E to the 0, anything to the 0 is 1, and e to the 1 is e, which means that, like, the points 0, 1, and 1e are on the graph, okay? Here's 0, 1. Here's 1e. Remember, e is like 2.7 or something. And then, hopefully you remember, like, kind of the shape of it. Okay, this is one of those graphs we should probably know. It's an exponential, so that'll help you remember it. Like, oh my gosh, like if I say this, right, guys? My stress is growing exponentially. It means it's just getting faster, like that. There's an exponential, okay? My stress is growing exponentially. All right, but this is what it looks like. Now, just taking e to the x. Whoa, get out of here. Okay, that was weird. Just taking e to the x, okay? What's the limit as I go to infinity? All right. As x goes to infinity, where's that shooting off to? I should put e to the x. Well, it's going to infinity. But what's happening on the other side of the graph? As it goes to negative infinity, what's happening? It's going to 0. All right. I mean, another way you could think of that is because, like, while you're not exactly allowed to do this, okay, this is not mathematically correct, but just think about this real quick. E to the negative infinity, it's like a negative exponent. We know that negative exponents can drop down to the bottom and become positive. So it's 1 over e to the infinity is like some giant freaking number, and that's going to end up going towards 0. Okay, so if we picture that graph, right, we can get these 2 statements, and that's going to kind of help us with the rest of these questions, okay? All right, check it out. Well, we just did this one. E to the negative infinity, it goes to 0 if you know what the graph looks like. Also, another way to think of it is like, oh, it puts 1 over e to a very large number. Okay, e to the positive infinity goes to infinity because we remember what the graph looks like. Okay, now let's do this. When you have a limit of two separate things, you can do them separately. Okay, so look. Limit is x approaches infinity of e to the negative x. Again, e to the negative x goes like 1 over e to the x, and if there's a huge infinity on the bottom, that goes to 0. Then I can do this one as a separate problem, and I can just add those limits together. So you're allowed to do the limits of both separately. You're allowed to do that. Okay, to infinity, we have degree of the top, degree of the bottom are the same, so we use coefficients. 2 over 1 is 2, so this limit is 2. All right, hopefully that idea makes sense to you. Okay, now let's look at this. Okay, guys, so this is actually pretty tricky. What I'm going to try to figure out is which of these grows faster. Does this one get really big, or does this one get really big? And that's going to help me figure out what happens as it goes to infinity, okay? Now, I thought I would look at the graph here, and you guys, this is actually really interesting, okay? So here's my graph of 2x squared plus 4x, that's the red graph, and then e to the x plus 3x squared. It looks like they're growing at the exact same rate. Look, they're practically growing together right here, okay? But let me tell you something, you guys. Exponentials grow very, very fast, all right? Like when COVID first came out, people weren't like, oh my gosh, the cases are spreading parabolically, or quadratically, right? Everyone's like, the cases are spreading exponentially because exponentials grow really, really fast. Let me change the window on this a little bit. Check this out. Okay, the red is the quadratic, the blue is the exponential. That one is going to infinity much, much, much faster. And the more I spread out, the more you can see that this one's kind of poking along, but this one is just shooting straight up to infinity, okay? So because this gets bigger faster and this one doesn't, it's going to end up going to 0 because you have a very big number on the bottom. So we'll discuss that concept a little bit more, okay? In class, we're going to go ahead and look at that assignment. So you guys don't have to do anything except for just make sure you got the notes done for this. All right. Great work, guys. Under a half an hour. Let's go.